here, we're going to have to take into account the fact that we're going to have equilibrium to start with, that's then going to be changed, and then we're going to reach a new equilibrium. So it sounds like it's a totally different type of question, but really instead we just have to take into account our initial concentrations of multiple things, that your initial concentrations are coming from an original equilibrium. So our initial is going to be coming from original equilibrium. And what we're going to be doing is we're going to be adding a strong acid or a strong base and seeing how the equilibrium is shifting. What are the new concentrations? What's the new pH? So this is going to be a real practical thing, something that you might do in the lab and something that you'll be asked to do in the lab. Figure out how much the pH would change of a solution if you added a certain amount of acid or base. This is also going to help us see the point of a buffer and what happens when you're in a buffering range and outside of a buffering range. So we're going to be using this to try to kind of sketch out titration curves and show what's happening, be able to choose correct acids or bases, and know how much we might need to add in the lab to to make a certain pH solution of a buffer. Because remember that buffers have like each acid has a specific Ka, and if you dissolve that, you'll get a certain pH, and depending on how much of it you dissolve, you can get a slightly different pH, but that's going to all be limited by the pKa, by what you put in, by the acid you put in. If you want to tip the scale more, well, then what you're going to have to do is you're going to have to add an external source of acid or a base. And so that's what we're talking about here. In order to do this, when you're adding an acid or a base, what you're going to be doing is you're typically adding the strong acid or a base. So it's all going to be dissociating. So we can think about it in terms of how many moles it's going to add pretty simply. But we can't think about things in terms of molarity very simply, because when we're adding the acid or a base, if we're adding it as a liquid, we're going to change the volume. And so we'll see another example where we're actually more practical with what we do in the lab, is instead of just adding an acid or a base to an already made buffering solution that's already at its final volume, we make it in a smaller volume, and then we adjust the pH, and then we adjust the volume, so we don't have to worry about the change in volume. But if you were to just drop some acid or base into a solution, or think about how a biochemical situation might be perturbed by the addition of an external acid or a base, well, then you don't have that luxury, and so you need to take into account the volume. And so we'll do an example where we're going to take into the account the volume, and then we'll do an example which is more like what you might be doing practically in the lab. We're going to need to figure out, okay, well, how many moles do we have in there originally? Or at least I'll show you an alternative where we can figure out kind of like the final molarity in terms of just if you were to dilute it, not considering it reacting. But when you have a strong acid or a strong base, basically all you're going to get is like a titration reaction to start with. And so all of that acid or all of that base is going to react with your weak acid or with your weak base. And the amount that can react is, well, whatever's limiting. So is it typically it's going to be like the strong acid or base you added that'll be limiting. And so basically all of it usually reacts. And then you just have to think about, okay, well, how much are you taking out of commission, and how much of the conjugate acid or conjugate base are you then generating? And so we'll go over an example of how this works. But it's really not as bad as it seems, thanks to that Henderson-Hasselbalch equation telling us, allowing us to kind of use that pKa value, as well as if we can find the concentrations of our conjugate acid and conjugate base using our ICE chart, and using the fact that, well, we're just subtracting a certain amount. It's this titration type reaction. We don't even need to do like solving for X. We can just figure out X based on whatever's limiting. To start by changing things into moles, or I'll show you a different way later, but basically the easiest thing to think about is to just convert it into your initial number of moles using that Henderson-Hasselbalch equation. If you know what the original pH is, you can figure out how much of each of the conjugate acid and conjugate base are in your initial mixture. Or if you were just told what's in there and it wasn't pH adjusted at the beginning, well, then you could just figure out the initial number of moles. Now you want to think about what you're adding and predict how the equilibrium will shift. First off, we need to remember that although we've kind of been ignoring it, at least formally, there are two equilibrium that are happening here. We have our water, and it ionizes to give us our H plus, which we can think about as H3O plus, and our OH minus. And remember that when we talk about water, we typically think about water as kind of being a constant because its concentration is so high. And in fact, we have very, very little of protons or of our hydroxide present just in normal water. And even when we add an acid or something like this, it's still going to be very small quantities compared to the amount of water that we have. Because they're such small quantities, though, basically a little change in them is going to change our pH drastically. So what's going to happen is that when we have our acid-base equilibrium for our conjugate acid and conjugate base, it can easily also disrupt this water equilibrium and therefore affect the pH of the solution, which relies on the overall proton concentration and overall hydroxide concentration. So, for example, if we take our weak acid, and we say that it's going to react with water, this is going to give us our conjugate base plus our H3O plus. So remember that we have this relationship in water where it's trying to reach its own equilibrium. And we have that relationship where we have that our Kw is equal to our proton concentration times our hydroxide concentration. And this Kw is basically a constant for given temp. And since it's a constant, well, it means that our H plus times our OH minus, that has to be constant as well. So if one of them increases, the other one has to decrease. And if one of them decreases, the other one has to increase. Now, the H plus can increase because you have a acid interacting with water to give you a proton. The OH minus can increase because you have a base interacting with the water to give you that hydroxide ion, which then will disrupt the balance, leading to an increase in your proton concentration. Let's look at this a little more explicitly. Now, what would happen if we added a strong acid? Well, if we add a strong acid, basically we're increasing our H3O plus. Le Chatelier's principle tells us that if we're adding a product, we're going to shift our reaction right to the left. And so basically we're going to shift towards our reactants. And what this means is that we're going to increase our amount of HA, and we're going to decrease our amount of A minus. So what we would end up with is basically we're going to get an increase in our conjugate acid and a decrease in our conjugate base. Now, you might be wondering about, okay, well, how is this affecting the water equilibrium? Basically, what's happening is that the protons that you add by adding that strong acid, well, they're actually also going to be interacting with your hydroxide ions that are in there. There aren't very many hydroxide ions in that water, so you're not going to be having, you don't have to worry about your acid kind of being siphoned off by all those hydroxide ions. But this is going to decrease the amount of your OH minus in the solution. When this happens, basically the water has to reach its equilibrium. And remember that when we're talking about the water equilibrium, we're talking about like Kw. And so it has to adjust, which is going to mean that it's going to increase its proportion of H3O plus in order to kind of compensate for this. As a result, your pH is going to decrease when you add that strong acid. Even though we're going to consider that all of that added acid that we add is going to be consumed, you're still ending up with an increase in your proton concentration because you're disrupting the water's equilibrium. Okay, so now let's see what happens if we were to add a strong base. So if we add a strong base, we need to remember that we're not adding the conjugate base. So just like before, if we add a strong acid, we were adding basically just free protons. We weren't adding our conjugate acid. Similarly, if we add a strong base, what we're doing is we're saying, okay, we have HA, plus OH minus. And now this is going to give us a reaction where basically this is going to react to give us our A minus. And in this case, it's going to give us water. So what's happening now is, well, we are deprotonating our HA, but we're not actually generating more protons. And so this is not going to increase our proton count. Instead, what it's going to do is it's actually going to decrease our pH. So what we're doing is we're adding a reactant in this case. We're going to shift things to the right. We're going to generate more of our conjugate base. And what's going to happen is that this OH minus, a bit of the OH minus that we add, it's going to, first things first, is going to react with the strongest acid in there. So it's not going to react first with your weak acid. It's going to react with those protons that are present in the solution. And then when it reacts with those, basically it's going to sop some of those up. It's going to decrease the proton concentration, and therefore you're going to get an increase in your OH minus concentration, and you're going to get an increase in your pH. So if you add strong base, then you're going to get a decrease in your proton concentration. You're going to get an increase in your OH minus concentration, because these have to balance each other out to equal your Kw. And then when we added strong acid, we were increasing our H3O plus and decreasing our OH minus. And remember that when we're increasing the H3O plus, we're going to be decreasing our pH. And if we increase our OH minus, well, then that water is going to have to re-equilibrate in order to compensate, because remember that water has its own equilibrium that it needs to reach as well. What's going to happen is that our acid and base, our weak acid base equilibria are going to be intimately intertwined with the water's ionization equilibria. And so this is why we have that for a weak acid base pair, we can say that our Ka times our Kb equals our Kw. So our acid dissociation constant plus our base reaction constant when it's the base is interacting with water. And so those are going to multiply to give us our Kw, which we could also take the P versions of these and basically say pKa plus pKb equals the pKw, which is equal to 14. And so we can, this way, we can find the pKb if we know the pKa, and vice versa. And those all have to sum up to 14. Once you've predicted how things will shift and you know what you're subtracting and what you're adding, you can go ahead and set up your ice chart in moles. So remember that a strong acid or base will basically all react with the weak ones. So basically you get a titration reaction where the limiting thing, so whether it's the strong acid or strong base, or whether it's the actual amount of that acid or base you have, the weaker ones that you have in your solution, one of those is going to be limiting. And so you'll basically be adding and subtracting that limiting amount as your X. And it'll make more sense when we look at the examples, but that'll be your X. And you don't even have to go and solve crazy quadratic formulas in order to find it. Then if you need those moles, molarity, you can go ahead and just convert it back to molar by multiplying by your volume. And remember that's in liters because molar is moles per liter. And then you can find the change in pH using Henderson-Hasselbalch. And so this is going to be one that I'll want you guys to know is like if you add if you add a certain amount of acid or base to a buffer, how is that going to change the pH? And we'll also look at, well, how could we kind of like do the reverse? Like what would, like how much of an acid or a base will we need to add in order to change the pH? And so we'll look at examples of both of those, but let's start by just doing a basic example. And just note that like if you don't need to solve molarity, if you just need to solve, say, the pH using the Henderson-Hasselbalch, you can use moles in the Henderson-Hasselbalch because basically since it's just a ratio, and if you're dividing by the volume to get the molarity in the first place, well, then you're dividing by the same volume on your top and your bottom. Those will cancel out. And so you can use moles or you could use molarity when you're using the Henderson-Hasselbalch. If we add 10 milliliters of 1 molar HCl to 100 milliliters of 150 millimolar acetic acid acetate, so that solution that we've been dealing with all along that we're really loving, at a pH of 5, what is the resulting pH? What is the concentration of acetate at the new equilibrium? So if in this question, we're given at a pH of 5. Now, if you see something that's saying at a pH of something, that should be a hint that you need to use the Henderson-Hasselbalch equation. And we're going to be using an ice table. We're going to be using that Henderson-Hasselbalch equation in order to figure out the original amounts of our acid, our conjugate acid and base. And then what we're going to do is we're going to figure out how things are going to change. Okay, so let's start by sketching out our initial situation. So we have an original equilibrium between our acid and our base. In this case, we're talking about an adjusted pH. So we're saying at a pH of 5, and this is what we just talked about before when we were talking about needing to use the Henderson-Hasselbalch in these types of questions. We're not actually going to have to use the Henderson-Hasselbalch here because we already used it. So we're just going to be lazy and use the value we already calculated. But that's how you would go ahead and you would find the initial concentrations. So remember that in this case, we have our acetic acid and we have our acetate, and then we have our protons. And importantly, this is from our HA dissociation and from external. So somehow you adjusted the pH, you added HCl, something like that. And so we're given this H3O plus that we have here is from all combined sources. So we don't even have to know exactly where it came from. We just have to know the value. And we can calculate that value based on the pH. So we can go, remember that relationship where we have the pH equals minus log of our H3O plus. So we can then say our H3O plus is equal to 10 to the minus pH. And then we can go ahead and we can solve this equals 10 to the minus 5.0, which is going to give us a value of 0.1234 zeros and a 1. Okay, so we're going to have this as our value. Now, that's a pretty small number. Let's see how big our other numbers are, and then we'll see whether we actually need to think about this H3O plus at all. Because if it's like more than an order of magnitude or so, it's not going to be, it's just kind of going to get lost in rounding. So we won't even have to think about it. But if it's bigger, we do need to think about it. So let's first just start off and think about how much of the acid and the acetate we have. And remember, at this point, we're still talking in terms of molarity. We calculated before that our acetate concentration was going to be equal to 0.093 molar. And now we need to figure out our acetic acid concentration. We know that our combined concentration of our acetic acid and our acetate is 150 millimolar or 0.15 molar. So we know that 0.150 equals our acetate, so 0.093 plus whatever our HA is. And so now we can figure out HA. And we get that HA, the concentration of our HA, is going to be equal 0.057 molar. Okay, so now we have these in terms of molarity. And now let's look and let's compare how much of the H3O plus we have compared to how much of that acid and the conjugate base we have. We can see that we have several orders of magnitude less of our H3O plus, so we're going to ignore. So we're just going to really small. So ignore here. And we're just going to here take it as about take as about 0. And we're going to use this in our ice table. But before we can put this stuff into our ice table, first we need to convert it to moles, because remember, we're going to have to do that because our volume is going to be changing. And it's not just going to be changing a tiny amount. We're going to be changing our volume by a whole 10%. So 10 mils is 10% of 100 milliliters. And so we're going to end up with a final volume of 110 milliliters. So we'll deal with that later. We don't need to worry about that right now, but we're going to have final volume equals 10 mil plus 100 mil equals 110 mils. And because everything is like molarities in terms of liters, this is going to be equal to 0.110 liters. And so we're going to use that volume later to convert things back to molarity. But for now, we're just going to leave things we need things in terms of moles, so we don't have to worry about the volumes, because moles doesn't care how much your volume is, but concentration does. So how many moles of these do we each have? So let's think about how are we going to convert between our molarity and our numbers of moles given the volume. So we know that our molarity is moles per liter, and we want to find moles. So we have moles equals our molarity times our liters. And in this case, our liters, what we're dealing with is the starting liters, because that's where this 150 millimolar was calculated from. And so that is going to be equal to our 100 milliliters, which is equal to 0.1 liters. So what we're going to need to do is we're going to multiply this by 0.1, and we're going to multiply this by 0.1. And so what we end up with is 0.0093 moles of acetate and 0.0057 moles of our acetic acid. Now that we have the number of moles, let's go ahead and stick that into our ice table, and then we can go ahead and we can look at how things will change. In terms of the changing, what we're doing is we're adding 10 milliliters of 0.1 molar hydrochloric acid. We need to figure out how many moles of that of H3O plus we're actually going to be adding. Because remember that the HCl is going to dissociate to give you H3O plus. And how much? Well, we have our 10 mils. So that's 0.01 liters, because remember, molarity is in moles per liter. And then we have 0.01 molar. And this is going to give us 0.001. And so this is going to be the amount of H3O plus that we add. Okay. And so now what's going to happen is that H3O plus isn't just going to hang around. It's going to react with base. So when we're dealing with a strong acid or a base, we're basically just going to have like a titration reaction. So that acid is going to react with as much acetate as it can find. And basically, if the amount of the acid that we add is less than the amount of acetate that's in there, all of our acid is going to react, and we're going to have some acetate left over. If, however, we were to add more of the acid than we have of our base, then all of the base would react and we would have some acid left over. In this case, we're adding 0.001 moles worth of our H3O plus. This can then react with our acetate. In this case, the acetate has a higher concentration, and we have more moles of the acetate. So this H3O plus is all going to react, and what we're going to be left with is it's going to subtract 0.001 from each of these. And then, but those are going, when they react, we're forming another acetic acid. So this is going to be a plus 0.001. So we have all of that is going to be going in, reacting with our acetate to form more of our acetic acid. Okay, so how is this going to affect our equilibrium? In this case, what we have is we have 0.0057 minus 0.001. Here we have 0.0093 minus 0.001. And here we have, we'll have 0 because we basically subtracted we've used up all of the acid that we added. Now, when we don't really have 0 of H3O plus, because remember we had a little bit in the beginning, but this amount that we add is going to be orders of magnitude greater than the amount that we had in the beginning. So we weren't considering it there. When we go to figure out the pH, we will be taking it into account here. But for the sake of these equations, it's not going to matter. Okay. So basically, now that we know how much we subtract, well, we have a simpler thing than we actually had before. So before we were dealing with x's, but in this case, we know the x directly, so we don't have to even use a quadratic equation. We can just do this math. So just shifting things up a bit so we can see more clearly, we can go ahead and we can do this math, and that we'll get that we have 0.0067 moles of our acetic acid, 0.0083 moles of our acetate, and kind of 0 of our H3O plus, although we'll see later that this is not going to be the value that we use to calculate the pH, because just how we were ignoring the amount of H3O plus in the water in the beginning, well, we're still going to have to consider the amount of H3O plus. And it will have changed. So there will be a change in that H3O plus value. So remember, we're adding acid. So we would expect that at the end of the day, we're going to have we're going to have more protons in that water. But it's kind of complicated, and we're going to figure out the pH based on the Henderson-Hasselbalch equation using the amounts of acetic acid and acetate that we have left over, not based on the H3O plus that we have in this table. And so we'll see that at the end, how we're going to actually do this. But for now, let's figure out the molarity of these things. Remember that to find molarity, we can divide our moles by our liters. And so we have 0.110 liters. And what we can do is then we can figure out that this is going to amount to 0.061 and 0.075. And note that depending on where you round, you might get 0.076, and that's what we're going to get later. But that's going to be, these would be your values here. So alternative strategy would be, instead of calculating the molarity at the end, we can actually calculate the molarity that would be present at the new volume first, using the dilution equation C1V1 equals C2V2. So basically here, what we'd be doing is, instead of setting up the ice chart in moles and then converting it, we're going to use the C1V1 equals C2V2 to figure out what the concentrations would be at the final volume. Not taking into account any sort of actual change in their proportions or anything like this, just taking into account that final volume and kind of thinking about, like, you're instantaneously adding volume, but not adding the acid. And so you kind of have to just go with it. But basically you can do the calculations based on that's there, and then not, instead of dividing it at the end, you just have to make sure that you're going to do it for all of the components of your reaction. So we can go ahead and we can set up our C1V1 equals C2V2. So our initial concentration times our initial volume equals our final concentration times our final volume. Word of caution, our V2, so our final volume, that's going to be our final volume. So that's the 110 mil. But these final concentrations aren't really the final concentrations. They're not taking into account the reacting. They're just taking into account the dilution. But if we do this, then basically what we can say is we can take the initial concentrations of each of these. And for the HCl, this is like the concentration that we're adding. It's not, remember, it's not present in the original mixture. So this will make more sense once we stick it in the table. But basically, we want to figure out what would the molarity be of these solutions when we just like initially mix them before they react. So we can get these values of 0.052 of our acetic acid, 0.085 of our acetate, and 0.0091 of our hydrochloric acid. And we can go ahead and we can plug those into our ice table. Once again, we can see that all of the H3O plus is going to react because it's going to be the limiting reagent. So for our change, what's going to happen is we're going to get minus 0.0091. We're going to get minus 0.09091, and we're going to get plus 0.0091. And now we can go ahead and we can figure out our change. Basically, we're just going to have 0.052 plus 0.0091. For our acetate, we'll have 0.085 minus 0.0091. And for our H3O plus, well, that's just all going to react, and this is going to give us 0. But note that this really isn't actually 0. It's going to be a small number. And so we're going to be able to figure out that very small number using our Henderson-Hasselbalch equation with our new amounts of our acetic acid and our acetate. Do these calculations, we can figure out the amounts of acetic acid and acetate. And remember here, we're already in molarity, so we don't have to worry about converting it afterwards. So taking into account differences in rounding, we get the same answers as before. And so now let's go ahead and let's try to figure out our pH using our Henderson-Hasselbalch equation. So if we remember that the Henderson-Hasselbalch equation tells us that the pH equals the pKa plus the log of our conjugate base over our conjugate acid. Okay, so now that we know the concentrations of our conjugate base and our conjugate acids, we can calculate the pH. So our pH is our same pKa that we've been talking about, that 4.8, plus the log of, we have that our acetate was 0.076, and we had that our acetic acid was 0.061. Now what we can do is we can go ahead and solve this equation, and we get that our pH is going to be 4.9. So does this make sense? Well, remember that we started with a pH of 5, and now we've reduced that. So yes, it does make sense. So if you were to think about it without taking into account that the pH had been adjusted at the beginning, you might be confused because you'd be like, wait, how is our pH higher? But our pH is higher, remember, because we started with the table stacked with having more of our A- than our HA. And so that's why we had to use the Henderson-Hasselbalch in the first place to get those initial concentrations. And once we knew the initial concentrations, well, now then we could figure out the final concentrations and then plug those in to get our final pH, which is 4.9. So we've gone down 0.1 in pH. But remember that this is a small change compared to what it would be if we didn't have any buffering capacity to begin with.